Hello everyone. This video covers section 10.9. So yes, we're gonna go back to doing Laplace transforms. This is the last section and it will be a good review of Laplace transforms. Now recall that if you have a Laplace transform, the operator actually is linear, and by that I mean this: the Laplace transform of f of t plus g of t is the same thing as the Laplace transform of f of t plus the Laplace transform of g of t. And we use this many times. Also, the inverse Laplace transform of f of s plus g of s is linear, so this is the same thing as the inverse of f of s plus the inverse of g of s. And we did this multiple times. Now here are the bad news. The Laplace transform, the inverse Laplace transform of f of s times g of s is not equals to the inverse Laplace transform of f of s times the inverse Laplace transform of g. So therefore the operator doesn't work for this case. It works for this, but it doesn't work for this one. For example, let's say the Laplace, you have this Laplace transform for the first function, and the second Laplace transform is equals to this. Okay. Then if you multiply both of them, f of s times g of s, you can see that the s will cancel, so you end with 1 over square plus 1. Therefore, the inverse Laplace transform of the product is the same thing as the inverse Laplace transform of 1 over s squared plus 1, which if you look to the table, this is sine of t. However, if you do the inverse Laplace transform of f of s times the inverse Laplace transform of g of s, we get the following. The Laplace transform of f of s, again if you look to the table, is equals to 1, and the Laplace transform of g of s, the inverse Laplace transform of g of s, is equals to cosine t. So therefore, again, just look at the table. If you forget this, how to find this. So the Laplace transform inverse of this one will be 1, and the inverse Laplace transform of g is cosine. And clearly, cosine t is not equals to sine t. So therefore, this shows that this is not the case. Okay, so then this brings us to the definition of the new stuff we're gonna do today. So here's the definition. Definition says the following: suppose that f and g are continuous functions on the interval 0 to b, then for any t that is inside the interval, then the convolution, which is going to be denoted by f star g of f and g is defined by this. So the convolution is defined as this integral. All right, so here are the good properties of this. All right, now let's try the following example. The question is asking you to find the convolution between f and g when f is equals to e to the t and g is just equals to t. Okay, so remember by definition, f convolution with g is the integral from 0 to t of e to the t minus tau tau d tau. Remember, we're integrating with respect to tau. You can switch this to a round and it should give you the same answer. We can also do the integral from 0 to t. This will be now t minus tau, and this will be e to the tau d tau. So it's up to you which one you want to use. We're going to go with this one. So then, since we're integrating with respect to tau, t is a constant in here. So you can take it out. So this will be e to the t times the integral from 0 to t of e to the minus tau times tau d tau. Now to integrate this, you have to do integration by parts. Here u will be tau, du is equals to the tau, dv is equals to e to the minus tau, and then b will be equals to minus e to the minus tau. If you plug it into the formula, you will get this. The e to the t is outside. This will be minus tau e to the minus tau. Then minus minus will become plus. The integral from 0 to t of e to the minus tau d tau. And once you integrate the whole thing, and you should definitely check this. This is minus tau e to the minus tau minus e to the minus tau, and the limits are from 0 to t. So you plug the limits of integration in, you will get the following. It will be minus t e to the minus t minus e to the minus t, then minus, you plug in 0, this will give you minus 0 e to the 0 minus e to the minus 0, which is just 1. So if you multiply this, you distribute, this will give you minus t, and then it will give you minus 1. And here minus and minus is plus, so this is plus 1 times e to the t. So this should be e to the t. Now here the question is just asking you to find the convolution. So that is the convolution, and you're technically done. However, from here, what will be the Laplace transform of f convolution with g? So therefore this is the same thing as the Laplace transform of minus t minus 1 plus e to the t, which will give you minus 1 over s squared minus 1 over s plus 1 over s minus 1. Now, if you simplify this, the LCD in here is s squared times s minus 1. So if you add this, 3 fractions, this one is the s minus 1. The second one is the s times s minus 1. And the last one, it only needs the s squared. And once you simplify everything, then you should definitely check this. This is just basic algebra. This is equals to 1 over s squared times s minus 1. Why is that significant? Well, remember that by definition, this is supposed to be equals to the Laplace transform of f times the Laplace transform of g. Well, the Laplace transform of f is equals to 1 over s minus 1, and the Laplace transform of g is equals to 1 over s squared, which is exactly the same thing we just got. All right, you didn't get that one. Here's a chance to redeem your sins. We're gonna try one more. All right, in this example, you are given 2 Laplace transforms already, and it should be obvious pretty much where they came from. Okay, so actually, let's do that. F of t clearly is e to the minus t, and here g of t is just equals to 1. Okay, The question is asking you to find this in two different ways. So first we're going to do this the way we used to do it before, and then using the convolution. So first let's do the old method, which is just partial fractions at the most. All right, so then for the old method, you want to find the inverse Laplace transform of 1 over s plus 1 times 1 over s. So if we do the partial fractions, this will be a over s plus 1 plus b over s, and this should equals to 1 over s times s plus 1, or s plus 1 times s. Once you solve for this, and we have done this multiple times, b will be 1 and a is negative 1, so you should check on that. So therefore this is the same thing as the inverse Laplace transform of negative 1 over s plus 1 plus 1 over s. Now we know that the inverse is a linear operator, so therefore this is the same thing as the inverse Laplace transform of this one plus the inverse Laplace transform of this one. Now we look to the table, but we already know what this is. This is equals to minus e to the minus t, and this one is just equals to 1. So that's the old way, which, remember, this can be very annoying if the partial fractions are not nice. All right, so now let's look to the new method, or the convolution. Okay, so recall that the definition means the following. If you want to find the inverse Laplace transform of the product, all you have to do is find the convolution of the two functions. Again, remember the f of t equals to e to the minus t, and g of t was equals to 1. So therefore this is equals to the integral from 0 to t e to the minus t minus tau times 1 d tau. Again, you can take out the e to the minus t, so this is just the integral of e to the, the integral from 0 to t of e tau d tau, which will be e to the minus, should be t. Then this part will be e to the tau from 0 to t, which will give you e to the minus t. This will be e to the t minus e to the 0, and this will give you 1. You distribute minus e to the minus t, which this is exactly the same as the answer here. Alright, so finally let's do an example where you had to solve a differential equation using this method. Alright, let's say that you want to solve this differential equation. The difference between this and all the problems we done before is that here you don't actually know what this function is, but you still can solve this in terms of the convolution integral. Alright, just like before, you're gonna apply the Laplace transform in both sides. So you're gonna apply the Laplace transform on both sides. Same thing we did before. So therefore, from here on the left side, we'll get s squared capital YS minus sy of 0. Just look to the table if you forgot the formula. Minus y prime of 0. So remember, this part is for this one. And then for the second part, just plus 16 Laplace transform of y. And then the other side, for lack of a better name, since we don't really know what this function is, by definition, this is just f of s. Here, for the initial conditions, alpha and beta are constants, just as they had been all along. So you plug it in, we end up with s squared ys minus s alpha minus beta plus 16 ys equals to f of s. Then if we factor the ys and move everything else to the other side, we end up with ys times s squared plus 16, and this is equals to s or alpha s plus beta plus capital F of s, which implies the capital Y, or the Laplace transform of Y, is equals to alpha times s over s squared plus 16 plus beta times 1 over s squared plus 16 plus f of s times 1 over a squared plus 16. Notice that this is the Laplace transform of sine for t. So therefore, you want to apply the inverse Laplace transform, or we need to have a 4 in here. So therefore, you divide by 4 here. So this is not new. We have done that multiple times. And you can do the same trick in here, multiply and divide, which technically is just multiplying times 1. Remember, anything times 1 is equals to itself. Alright, so therefore from here, if you want y of t, this is going to be the inverse Laplace transform of s or alpha s over s squared plus 16. Or you can actually just put the alpha outside, so it will be alpha here. Then we do the same thing with this one. It will be beta over 4 times the Laplace transform of 4 over s squared plus 16 plus the inverse Laplace transform. The 1 4 goes outside, and now this will be f of s times 4 over s squared plus 16. So this will be, well, this is f of s, clearly. And this will be g of s. If you look to the table, you should see right away that this is alpha times all of this is just cosine for t. Then you have beta over 4. This one is sine for t. And then you'll have the 1 4. And then since we don't know what this is, we cannot really find this inverse transform, but you can write it in convolution integral, in a convolution integral. So this will be the integral from 0 to t of f of t minus tau times the second function, which is sine of 4 tau d tau. Now, since you don't know what f is, you can integrate this. So once you get to this point, you're done. And that's it.